Hello everybody, my name is Patrick Halder. I'm a researcher at CF and I'm within the Cyber Physical Systems group at Technical University of Munich. Today I present our paper on minimum violation velocity planning with temporal logic constraints. My co-author is Matthias Althoff. Motion planning for autonomous agents requires to comply with a variety of constraints like safety, traffic rules, mission specifications, and others. However, we cannot guarantee to satisfy all constraints simultaneously in all possible scenarios, for example, due to the misbehavior of other traffic participants. Nevertheless, in such situations, it is of great importance for a motion planner to produce explainable and justifiable actions. And exactly this challenge is tackled by minimum violation planning, where less important constraints are deliberately ignored, while the satisfaction of more important constraints is maintained. In this work, we present a minimum violation velocity planner, which uses constraints formalized in signal temporal logic, and which violates these constraints as less as possible in the sense that important constraints are violated last. An application of our planner is ZF's autonomous shuttle, which moves along a predefined path by using a magnetic positioning system according to an online computed target velocity profile. Let us start with some preliminaries. In this work, we use signal temporal logic. In contrast to other types of temporal logic, STL allows a reasoning over real-value trajectories, which makes it highly suitable for motion planning tasks. STL is defined according to the grammar shown here, where phi is a STL formula and mu is a predicate. U is the temporally bounded until operator and S is the temporally bounded since operator. Based on this grammar, we can derive other operators like a globally or finally operator. STL comes with a quantitative semantics which is called robustness, and it quantifies the level of compliance or the level of violation of a trajectory with an STL formula. Let us have a look on an example formula phi, which indicates that globally the velocity must be below a certain velocity threshold. The robustness can directly be derived from this formula. You can see that the robustness is positive when we drive slower than allowed, and if we drive faster than allowed, then the robustness is negative. Next, let's talk about rules and rulebooks. So first, what do we consider as a rule? With the term rule, we summarize different types of constraints, which can be example safety, traffic rules, mission specification, comfort requirements, and many more. In this work, we formalize rules in signal temporal logic. Then we can use so-called rulebooks to rank the rules according to their priority. In general, rulebooks prioritize the rules in pre-orders, and they induce also a pre-order on a set of candidate trajectories. On the next slide, we will see an example for this induced order. In this work, we use totally ordered rulebooks since they induce the lexicographic order on a set of candidate trajectories. As a quick reminder, so how does a lexicographic comparison of vectors work? The decision if a vector A is lexicographically smaller than vector B is based on the lowest non-equal element of the vectors. So in the left example here, vector A deviates from vector B on the first level, and thus A is lexicographically smaller than B. In the middle example, the first level entries are equal, but A is smaller on the second level entry than B, and thus A is lexicographically smaller than B. In the right example, the vectors are equal. Okay, so let us now have a look on the promised example. Depicted here is a scenario where the Ego shuttle is surrounded by two other vehicles and the yellow vehicle performs an illegal cut-in maneuver in front of the Ego. Imagine there are three possible maneuvers or trajectories to handle this scenario by the Ego vehicle. Let us now use a rulebook B1, which states that it is more important to keep a safe distance to the front than to keep a safe distance to the rear. This rulebook now induces the order which is presented here on the three trajectories, where tau 3 is the best one since it does not violate the more important rule of a safe front distance, likewise tau 2. But additionally, tau 3 violates the less important rule of keeping a safe distance to the rear, less than tau 2. If we now flip our rulebook, then the new best trajectory is tau 1, since it is the only one which satisfies the rear safe distance rule, while the other trajectories do not. Let us now come to our formalized STL rules. In total, we formalized 32 rules, which are inspired by German traffic law and by our previous works. Here we present three of our rules. The first rule prevents colliding with other vehicles. Formally, it states that it shall always hold that when an obstacle is of type vehicle and there is a geometrical overlap between the ego and this obstacle, then the relative velocity between them shall be zero. On the one hand, this describes to prevent collisions with this vehicle, and on the other hand, it describes that if a collision is unavoidable, trajectories shall be preferred where the relative velocity is smaller. The second rule handles stopping at traffic lights. It punishes driving into the intersection if a traffic light is crossed during a red phase. And the last rule is about scheduling and states that the ego vehicle shall be at least once in a certain position interval at a certain point in time. Okay, we now present our approach for minimum violation velocity planning. First, we redefine the temporally globally operator. We do this in such a way that we only consider the negative robustness of a trajectory regarding a rule, and this means that we are only interested in the level of rule violation of a trajectory and not on its level of satisfaction. Also, we sum up the negative robustness over a certain time horizon, which has the effect that a violating trajectory, which returns into a rule-compliant state, produces less negative robustness than a violating trajectory, which remains in a rule-violating state for longer time. All of our formalized traffic rules start with the globally operator. Then we order our STL rules hierarchically in a totally ordered rulebook. And we use the robustness of these rules as the costs in our optimization problem. We then search for the lexicographic optimal velocity profile by solving a so-called lexicographic optimization problem. Our velocity profile is computed along a predefined reference path gamma, and we use a discretized second-order point mass model as longitudinal motion model. We solve the mentioned lexicographic optimization problem as follows. First, we discretize the configuration space as a lattice graph and sample time, position, and velocity equidistantly. Then we perform a lexicographic A* search in this lattice graph. In the graph, the traversal costs of a trace are based on the robustness regarding all rules in the rulebook, which means in our case we have tuples of robustness values that contain 32 single robustness values per trace. Then these robustness tuples of competing traces are compared lexicographically. The minimum violation velocity profile corresponds then to the lexicographically best trace in this lattice graph. Let us have a closer look on the mentioned robustness tuples. So each trace in the lattice corresponds to a robustness tuple which contains the 32 robustness values for our 32 STL rules. Additionally, we can easily define a heuristic robustness for simple rules which have the form that is presented here. The reason is that because for these minimum and maximum velocity rules, an expected robustness can be easily calculated using a simple forward simulation with the minimum and maximum possible vehicle acceleration. For the remaining rules, we set the heuristic robustness simply to be 0. Resulting, we get a tuple containing 32 heuristic robustness values for a trace. The total robustness of a trace is then simply the sum of the trace and the heuristic robustness. As already explained, instead of using scalar cost values, our A* algorithm uses the robustness tuples. In order to find the optimal trajectory, the algorithm compares these tuples lexicographically. Presented here are two example tuples where the robustness tuple corresponding to trajectory tau1 is lexicographically smaller than the one corresponding to trajectory tau2, and thus tau2 is better than tau1 as tau2 violates the rules lexicographically less than tau1. But you can already see an issue here. We have to evaluate 64 rules to generate the robustness tuples. But for the lexicographic comparison, this is actually not necessary. Let us compare the tuples again. We see that the robustness values for the first two rules are equal, so we continue with the robustness for the third rule where the values already deviate. According to the already presented lexicographic comparison rule, this already defines the relation between the two tuples and we don't have to look at the values which are to come below. We make use of this in our algorithm to reduce the number of necessary rule evaluations and save computation time. We can further reduce the number of necessary rule evaluations by using a custom priority queue. In contrast to classic priority queue approaches, our algorithm does not maintain a totally ordered list of elements. Our main idea is to assign the priority queue elements based on a lexicographic comparison into unsorted containers, which we call buckets. This is very similar to the well-known bucket sort algorithm and happens in the adding step of the queue. And then subsequently we only search the most promising bucket based on the so-called lexicographic sort algorithm for the currently best element. This happens in the popping step where the best node is extracted from the queue. Let us now look at some example scenarios from the Common Road benchmark suite. On the left side, you can see the scenario where the green ego vehicle moves according to the minimum violation trajectory, and the yellow and light blue ego vehicles correspond to two lexicographically worse trajectories. The corresponding velocity profiles are shown in the right top figure. In the right bottom figure, you can see the scaled robustness of all 32 STL rules, and you can see how the negative robustness increases when the time horizon also increases. The robustness values at the last presented time step are the ones which are used to compare the trajectories lexicographically, since they correspond to the complete planning time horizon. In this scenario, the ego vehicle passes a stop bus at a bus stop, and it already violates some rules at the initial time step. As a result, the ego vehicle cannot satisfy the safe distance rule phi 7 and the passing of buses rule phi 11. But as you can see, the green minimum violation trajectory minimizes the negative robustness for these rules by performing the harshest braking maneuver. In our next scenario, an obstacle performs a cut-in maneuver in front of the ego vehicle. The result is an unavoidable front bumper crash. You can see that all three trajectories violate the stop after crash rule, since all continue driving for some time. However, the green trajectory produces the fastest stopping maneuver and also minimally blocks the pedestrian crossing. Note that the blue trajectory does not block the pedestrian crossing at all, but since it violates the stop after crash rule more than the other two trajectories, it is lexicographically worse. In our last scenario, an emergency vehicle on duty is approaching an intersection, but the ego vehicle is blocking its way. Since we specified in our rulebook that it is more important to not block an emergency vehicle on duty than to remain stopped at a red traffic light, the green optimal trajectory drives into the intersection, but only as fast and as far as absolutely necessary. In contrast, the orange trajectory blocks the emergency vehicle and the blue one drives much more into the intersection than necessary. Let us now look at the performance of our algorithm. This table shows the number of rule evaluations in R and the computation time Tc for the three previously presented scenarios. We compare a pure R* algorithm with our adapted approach with the minimum number of rule evaluations. You can see that we can reduce the number of rule evaluations. However, the difference in the computation times is not so large as for the number of rule evaluations. This comes from the fact that we mostly reduce the number of evaluations for low priority rules, which are in our application not so costly to evaluate, compared to high priority rules where collision checks are involved. But overall, we believe that the calculation times are quite reasonable for a prototypical Python implementation. In summary, we present a minimum violation velocity planner, which combines a lattice representation of the configuration space with a lexicographic A* search, utilizes the robustness of rules formalized in STL, reduces the number of rule evaluations, and finally produces interpretable and reasonable outputs for complicated scenarios where many rules must be violated simultaneously. Let us conclude with some future work. First, we want to develop more complex and realistic rules. Second, we want to deduce an automatism to derive heuristics which are independent of the type of rule. And last, we want to extend our algorithm to the more general case of pre-ordered rulebooks. This concludes my presentation. Thank you very much for your attention.